Okay, let's see if this is working now. Okay, perfect. Now it should be working now. Okay, you see movement. Excellent. Hi, everyone. Excellent. Okay, perfect. Welcome to MAE 106, Discrete Mathematics with Probability. My name is Richard Kohar, and this is Lecture 20 with a little bit of a bump start, but we're going to be talking about permutations with repetition of indistinguishable objects. Perfect. What are we? Got lots of, well, this is a cool topic. And before we'll start, just some important things to announce. So just to announcement. Thank you everyone for sticking in. So next week, November 2021 is our second test. Okay. Let's see if we can fix this. Okay. Okay, hopefully that helps. Okay, perfect. So we have an announcement on the 5th of November. On the 5th of November 2021, so that's next week, Friday, we're going to have test 2. And just to be sure, what we'll be covering is material that we did in lectures 12 through 17 inclusively. So that means it includes 12 and 17. And we also will cover the material and questions that are on assignments 4 through 6 inclusively. And this will be very similar to what we did previously. We will do it over Zoom. You'll scan it in. I will try to... Thank you. I appreciate everyone for handling the delay, but hopefully everyone got back their test. Test 1. The marks, the histogram is provided on Moodle and the average as well. I won't announce that publicly again, but you can check that out. And then next week I will also have some office hours. So again, those are over Zoom as well, and you can check on Moodle again. Let's see Moodle. So permutations we've considered thus far have been involving those of distinct or distinguishable objects. So given that we have two objects, we can discriminate between them based on some property of interest. And in many cases, we are interested in finding the number of permutations of a set of objects, but sometimes they might not all be distinct. So there we go. So we can say how many permutations of the word data are possible. Well, somebody might say, what somebody might think is that, okay, well, there's 4 letters. And so for the first choice, that there is 4. And then for the second, there's 3. For the third position, there would be 2. And then lastly, there's just 1 left over for the 4th letter. So again, that would be 4 factorial, or you could write that out as 4 permute 4. But what that means is that you will have some repetition, because we have the A and the A, and those are not distinguishable. So let's see, that would be 24. 4 times 3 is 12, times 2 is 24. But we're overcounting. Because for instance, let's say if I write out, here's data, and I write, if I think of it as distinguishable, there's an A there, and let's think of another one over here. Here's an A. Okay. You can change the order there. We have data. Okay, but this is, again, that's assuming that these two are distinguishable. But let's say that I don't have color or anything like this. I'm going to photocopy it. Well, then I'm just left with data and data. If there are A's that are distinguishable, the A's are not distinguishable. Okay, so we're overcounting using this 4 permute 4. So instead, we need to refine what we want to find. So what we need to do is count the number of distinguishable permutations. Of distinguishable So to do that, what we can is take cases. We can break down the problem in the following cases. So we'll take some cases. So the number of ways to select 2 A's is 4 choose 2. Okay, and so we can just apply our formula for that. So that's the n, choose r, so that's n over n minus r factorial. So I'm left with 2 times 3, which is 6. The number of ways to select 1D from the remaining 4 minus 2 letters. So that's 2 choose 1, which means that that's 2. And lastly, the number of ways to select 1t from the remaining one letter is 1 choose 1. So that's 1. So using the multiplication principle, by the multiplication principle, what we have then is 6 times 2 times 1, which equals 12. And if you don't believe me, what I do have is this. So this is what we have. So what ends up happening is here is the 24 permutations that we had. Okay. And so there's 1, 2, 3, 4, 5, 6 by 4. So 6 by 4 is 24. But you notice that if I change the order, the A and the A here, that gives me a repetition. So again, this is not distinguishable. So you can cross that one out. And again, you write DAAT, you can change the order. So then you get a repeat, a repeat. So what ends up happening is that we've overcounted basically by 2, by a multiple of 2. Okay, so let's say that there's the RMC, and we'll say the soccer team. We'll say that there are 7 games in total. And what we'll say is that they have 3 wins. They'll have 3 losses. And let's say 1 tie. So the question would be, how many ways can 3 wins, 3 losses, 1 tie happen for the 7 games. So again, we have the issue of that we have 3 wins. Those are 3 indistinguishable things, objects. We have 3 losses. Again, those are indistinguishable. And 1 tie. So the same thing happens. What we'll do is we'll just take cases. So we start off with 7. And we're going to have the 3 wins. So we're going to have 7 choose 3. Again, the order doesn't matter then. So that's for the 3 wins. Then, so you can think of the multiplication as and. And then there would be 7 minus 3. And there's going to be 3 losses. And lastly, you would have 7 minus 3 minus 3. And you would have 1 loss. Or sorry, 1 tie. So you would have 7 choose 3 times. Then you would have 7 minus 3. So that's 4 choose 3 times 1 choose 1. Okay, so this is a good time to also remember what our Pascal's triangle is. So I can kind of quickly generate. This question is inaccurate. There is no possibility of. Okay. That's cold. Have you been outside? It's starting to get cold out there now. So 35, 21, 7, 1. All right. So what I've done is I've gone up from the 0 objects up to 7 objects here. And again, that would be 7 choose 0, 7 choose 1, all the way over to here's 7 choose 6, 7 choose 7. Wouldn't the top be 1? Somebody is writing. Oh, somebody's writing. No. Wouldn't the top be 1, then 1, 1? Yes, we can do that. Yes, yes, yes. There we go. Thank you. So again, I'm generating. So 1 plus 1 gives me 2. If I look at this, here's 1 plus 2 gives me 3. If I look down here, let's say 6 plus 4 gives me 10. So we're going to look for the 7 choose 3. So that's 0, 1, 2, 3. So that's 35 times, and now I need to look for the 4. So that's 0, 1, 2, 3. So that's 4 choose 3, which is 4. And then I need to do 1 choose 1, which is 0, 1. So that's just 1. Then the 35 times 4 is 140. Okay. So there's 140 ways that the soccer team can have 3 wins, 3 losses, and a tie. So what we can do is we can summarize this using what we call a multinomial coefficient. So we had the binomial coefficients like here, but let's go with a multinomial. Just a second. Multinomial coefficient. So if you had n total objects, and you had n1 objects that are alike, you had n2 objects alike, all the way up to nr objects alike, where basically the sum of these, n1 plus n2, all the way up to nr, equals n. Then the number of distinguishable permutations is, so we start out with n factorial divided by n1, which is the number of objects alike, n1, times n2, dot, 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 so that's multiplication still, nr factorial. Okay, so we come up with this symbol. Instead of writing with all these little exclamation points, we use this. We use n, n1, comma, n2, comma, dot, 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 all the way up to nr. And that, ladies and gentlemen, is what we call the multinomial coefficient. Okay, so if I wanted to think about this soccer player, the soccer team, sorry, I could have also written it as a multinomial coefficient. So I could have also written it as, I have 7, and then I have 3 wins, which is 3 objects alike. So there's 3, comma, 3, comma, 1. Which then I can express as 7 factorial over 3 factorial, 3 factorial, 1 factorial. So again, 3 plus 3 plus 1 gives me 7, so that I've got all the objects in total. Then I have 7 times 6 times 5 times 4 times 3 factorial. So the 3's factorials can cancel. I can divide the 6 goes into 3 twice. And then I will cancel out the 2 with this one up here, so that I'm left with 7 times 5 times 4, which equals 7 times 5 is 35, times 4, which again is what we have down here, which is equal to 140. That way is a lot easier. So yes, there is lots of ways of counting the same thing. So here is solution 1 that we did. And then over here is solution 2. But you can see that we have the binomials, and we had many of them, which is why they kind of gave this nickname or the term multinomial coefficient. Yes. So again, some people find one way easier than the other. Okay, so let's do an example. Let's see, let's think of, does anyone have a word that they want to use that has repeating letters in it? Scissor, assassin, soccer, kayak. Okay. Okay, yeah, let's use soccer. Swedish pop, ABBA, radar. Well, okay, so ABBA and radar, those are palindromes, albatross. Let's use soccer. We can quickly do this one. How many distinguishable permutations are there? So in total, there is 1, 2, 3, 4, 5, 6 letters. And then we have one S. I have one O. 2 C's. 1 E. And 1 R. So that means that I have six letters in total. I'll have one S, one O, 2 C's, 1 E, 1 R. So really that's 6 factorial over 2 factorial. So we can cancel that, so that I'm left with 6 times 5 is 30, times 4 times 3. So that's 30 times 12. So 12 times 3 is 36 times the 0, my 0 for my placeholder, so I have 360. Distinguishable permutations. So it's kind of a soccer. Same thing we can do assassin. So 1, 2, 3, 4, 5, 6, 7, 8. There's 2 A's. There's 4 S's. One I and 1 N. So that means that I'll have 8 letters in total. I have 2 A's, 4 S's, 1 I, 1 N. Okay, so then you have 8 times 7 times 6 times 5 times 4. I still have the 2 in the denominator, 2 times 1, so let's get rid of here. So 4 times 7 is 28, times 6 times 5 is 30. Then 28 times 3 is 84. And then add the 0 to get me 840. Did I do that correctly? Make sure that I've... Perfect. Okay, so we did the permutations with letters. Okay. Let me grab one more sheet. So let's say that my house is 3 blocks south, and let's do 5 blocks west. From a grocery store. How many paths can I take from home to the store if I only travel north and east? Okay. So here's the solution for this. The first thing we should do is draw a diagram. Let's use brown because it's like a road. So let's draw a grid. So I have 3 blocks south and 5 blocks east. Go down 1, 2, 3. And then we're going to go 5. 1, 2, 3, 4. And let's do 5. Let's do it like that. Okay, so my house would be 3 blocks south, 1, 2, 3, so that's going down, and 5 blocks west, 1, 2, 3, 4, 5. So there's my home. And over here is my house, or sorry, my store that I go to. How many paths can I take from home to the store if I travel north and east? Okay. So as we're constructing this diagram, we can already begin to see acceptable paths from my house to the store. I could go like this. That's an acceptable path because I'm going east, north, east, north, north, east, east. Let me write that out. So what I've done here is I've gone east, north, east, north, north, east, east, east. Okay? Or I could go could go this one, north. That's one way. So I could go north, north, then east, 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 and then north. Okay, this is going to take too much time if I keep doing what I'm doing right now. But 1, 2. I could go east, 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 north, north, north. Does anyone see any pattern yet? So that's the idea, is when we're doing problem solving, we're looking for patterns, you know, over 3, and yes, yes. Oops. What we see then is that all the paths that I'm taking to get from my house to my store, there's 1, 2, 3, 4, 5, 6, 7, 8. There's always 8 letters. Okay, there's always 8 letters. And what I also notice is that I have 1, 2, 3, 4, 5. There's 5 E's and 3 N's. And it doesn't matter which one I picked. Okay, I've kind of grouped them all here. So there's the 5 E's and the 3 N's. But here's 1, 2, 3 norths. 1, 2, 3, 4, 5 easts. And same thing up here. 1, 2, 3. 1, 2, 3, 4, 5. So what we've done is we've converted our problem into a problem that we have already solved. So we've broken it down. We've converted it now to basically how many distinguishable permutations of a word. In this case, it's this weird looking word here. MAE. And we can break it down to this. So, and I think that's what Mr. Hugo has said. So, we have 8, and then we have 5 E's and 3 N's, which is equal to 8 factorial over 5 factorial over 3 factorial. And I'll cross out this. Oh, did that? No, it didn't show up very well on camera. There we go. So the 6 cancel. 6 divided by 3 is 2. The 2 canceled out with this one. We cancel out the 5 factorial. So what I'm left then with is 8 times 7, which is 56. Ways, paths from home to the store. Now, I do believe that there is a, so this is there's one way of doing it. So what we've done, this is kind of like solution 1. what I can do over here is solution 2. So again, I'll draw out my so there's 1, 2, 3. 1, 2. So there's 1, 2, 3, 4, and 5. So starting from here is my house. Here is the store. So this is another way of doing it, which is to get to this point here and this point, which is very similar to what we did previously with Pascal's triangle. There's one way to get here and one way to get there. And to get to here is 2. So there's one path to get there and one path to get there. So that's 1 plus 1 is 2. There's one way to get here as well. One way to get there. 1, and same thing, 1 here. So to get to this point right here, there is one path, and then there's 2 paths to get there. So 2 plus 1 is 3. So I have 3 paths to get there and 1 path to get there. So there's 4, 5, and 6. So again, 2 plus 3. Then I have 3 plus 3 is 6. 6 plus 4 is 10. 10 plus 5 is 15. And then I have 15 plus 6, which is 21. So there's 1, 2. Here's that last one. 1 plus 3 is 4. 4 plus 6 is 10. 10 plus 10 is 20. 20 plus 15 is 35. And 35 plus 21 gives me 56. And again, that's a very similar way to how we had done this with Pascal's triangle. So it was similar to how we constructed Pascal's triangle. And so there's 2 different ways of doing it. So that's the end of that example. But we had done it where we converted it to like words, and from that we used a multinomial, came up with 56 ways. Or you could think of it as breaking it down like Pascal's triangle, thinking about it as in terms of paths, and we worked all the numbers up to the store and gave us 56. Okay, I hope that was fun, and thank you all for tuning in on this Friday afternoon. If you have questions, feel free to send me an email at rmc.ca. We have office hours next week. And until next time, take care, and I'll see you on Tuesday.